Let's practice balancing a couple more reactions, and as we go we make it a little bit more complicated. In the end, it's going to take a little bit of practice on your end, and so it's up to you to practice this and be quick enough about it for an exam. Here we have sulfuric acid and sodium cyanide, which are both aqueous, meaning we have ions that are dissolved in water, right? And so these two react to form hydrogen cyanide and sodium sulfate. And if you look at the polyatomic ion here, the sulfate, you realize that it stays together and does not change chemically, so we can treat it as a single atom the same way we would treat chloride or sodium. And the same thing is true for sodium cyanide, which makes balancing this reaction very easy and quick. I've just rewritten it down here without the phase labels, so I have a little bit of room to put my stoichiometry labels in, my coefficients. Pick either hydrogen or sodium, it doesn't matter. If you ever follow one and follow through, as in, run into trouble, if you do start with 2 here and you fix it there and you run into trouble, you can always start over and use a different atom. But I'm just going to use sodium. We have 2 on the right and 1 on the left, so we put a 2 in front of it. As I said, that'll take the cyanide twice. We can treat it as a unit, so we have 2 cyanides on the right. We have 1 on the left on the reactant side and 1 on the product side, so we put a 2 in front of it. So now we have 2 hydrogens, which is what we have here for this sulfuric acid. This is, by the way, called a double exchange reaction, right? Because we are simply exchanging, whichever way you want to look at it, partners here. We switch the hydrogen and the sodium, and then we just have to pay attention to the charges here, right? Hydrogen, cyanide is -1 and sulfate is -2, so that's the reason why we need 2 sodiums to bind with sulfate instead of 1 over here, right? And so that's something important for you also to remember, the polyatomic ions you learned in the previous chapter, and that's kind of why I said if you know them, if you recognize them, it's going to be a lot easier for you to make it through the next couple of semesters of chemistry. Looking at the next reaction, this is aluminum sulfate. Again, this is dissolved in water. Both of those are aqueous, so we have ions, and in this reaction here we get a precipitate, a solid precipitate here, aluminum hydroxide. I'm going to point out the charges and the ratios of your products one more time, although you should know that back from when we were learning about naming. Here we have sulfate, which has a -2 charge, and aluminum, which has a +3 charge. That's why they are in a 3:2 ratio. And so when we switch the cations out, we get a different ratio here, right? So hydroxide's -1, that's why we need to have 3 of them, but that's enough. So down here I have them without phase labels, and so we can do the same thing. We have sulfate here that stays together and hydroxide that stays together. And we can start with aluminum. That might be the easiest. We have 2 over here, so I'll put a 2 in front, which now furnishes or makes 2 times 3 hydroxides. That's 6 hydroxides. I come over here, fix the hydroxides to make 6 here. So that's 6 hydroxides, but there's a 2 here, so we just need 3. 3 times 2 is 6, and we just balanced another reaction. This is a combustion reaction, mentioned them more than once. These are a little bit different, right? So every time you see a hydrocarbon, C2H6, C12H55, whatever, something that is CXHY, meaning you can have a number of carbons and a number of hydrogens, and it reacts with oxygen. It's called a combustion reaction. You're burning it, it's releasing energy, and so you get carbon dioxide and water. It is beneficial for you to follow these rules. In this case, what you do is, instead of balancing carbon, right, you start with carbon, right? So you have 2 carbon, you put it over here. Instead of then looking at oxygen and coming back to fix it, you ignore that. And the reason for that is that your product has both of your products have oxygen in there. So the rule is, number 1, fix carbon. Number 2, fix hydrogen. Number 3, fix oxygen. Okay, so you fix the carbon, which we did here. I have 2 carbons. Leave the oxygen alone. I have 6 hydrogens. So I'm going to need a 3 over here, right? 2 times 3 is 6. Then I add up all of the oxygens. 2 times 2 is 4 oxygens. 4 times oxygen plus 3 oxygen. So that makes it 7. Then I come over here and I do the same thing I've done before. I use 7 halves. And technically we are done. However, what we have now is we have to fix this. We did do the same thing. We multiply through by 2. And so that means you have 2 times C2H6 plus 7O2 produces 2 times 2, which is 4 CO2, and 2 times 3, 6 H2O, and this is balanced. We're going to do the same thing for C5H12. First we balance carbon, so we need a 5. We ignore the oxygen. We have 12 hydrogens, so we need a 6 over here. And then we add up all of the oxygen, so 5 times 2 is 10 times oxygen, and 6 plus 6 equals 16. Here's a 2, so we need half of that. That's 8, and in this case we don't multiply through by 4 because that's an even number, and we can just write down that 8. So this is balanced. You should practice a few of these, that's for sure. Sometimes what you will see instead of a reaction arrow, and this is just you balance it the same way, it changes nothing. This just means that there's an equilibrium here, that instead of, see, when you burn a hydrocarbon, when you burn a piece of wood, there's no going back, right? When this reaction is done, you will have, let's say you have 100 grams of C5H5. When you are done with this reaction, you have 0 grams of it left. It's all burned. It all turned into carbon dioxide and water. It is a reaction that goes to completion. The same thing is true with a piece of iron that rusts. Once it's rusted, it doesn't go back. Now, these reactions here are at equilibrium. That means they never go to completion. They can shift from one to another here. So this is the so-called Haber-Bosch process, the manufacturing of ammonia, which was developed in the 40s, and a true breakthrough in the development of fertilizer, because most of the fertilizers are nitrogen based. Well, all of them are nitrogen based, and nitrogen fixation was an issue, but that's beside the point here. That you balance it in the same fashion. Just understand that this will not go to 0 grams and 0 grams. This will always be at some sort of equilibrium, but this will be more thoroughly addressed in chapter chemistry in the second semester of chemistry. Forget about the quiz. This is an online class, no quiz. Okay? Shifting gears just a little bit before we do that. How do you know a reaction takes place? Kind of hinted at it already. You will see a visual, you get a visual clue, or you can feel it, right? Like if heat is given off, you can feel the change in heat. If something gets colder, that's an indication of chemical change. The reaction that we had in the beginning, lithium thrown into a glass of water, will form hydrogen gas. So the gas formation is an indication. We had a reaction where aluminum hydroxide formed a solid, so you would actually see a white solid forming, and then so a solid forming, a precipitation occurring, a color change is a good indication of a chemical reaction. Of course, a lot of reactions are either endothermic or exothermic, meaning they take up heat or they give off heat, and you can always feel the change in heat. Okay, so now we are going to look at those coefficients. Here we have a balanced combustion reaction. C8H18 is another hydrocarbon. For the sake of argument here, or just so to make my life easier, I don't like to say CH18. I'm going to call this octane. And you know what? that's actually not a bad name. If you think about it, you've seen an octagon, right? An octagon is a stop sign. The prefix oc means 8, right? And so to call this octane, it has 8 carbons, is not a bad thing, right? But that's again beside the point. Little side note, some extra information that you never knew you wanted. Anyway, this is already a balanced combustion reaction. You know how to do that, and that's not the point. But what do these coefficients really mean? Well, they can mean a number of things. We can simply say that we have one. If we have this means just we have 2 units, okay? And so we call this octane. So we need 2 octanes to complete this reaction. In order for 2 octanes to react completely, we need 25 oxygen molecules, right? So we're going to call these molecules. So C8H10 is an octane molecule. O2 is an oxygen molecule. CO2 is a carbon dioxide molecule and a water molecule. That just means like one water molecule, you just have one H2O, which is of course not a whole lot. It's very tiny and hard to weigh out, to measure out, so we usually use the molecular weights, which scales this whole thing up by Avogadro's number, if you remember that, right? And so, but when this reaction goes to completion and the law of definite proportions and conservation of mass, everything is preserved and followed, we need the octane to oxygen ratio to be 2 to 25. Right? So in order for this reaction to occur, we need 2 molecules of C8H10 and 25 of O2, which will then exactly produce 16 molecules of CO2 and 18 molecules of H2O. And if we wanted to scale that up into something we can measure, then we multiply those factors by moles, right? So then we can also argue that 2 moles of C8H18. So now we have, instead of 2 molecules, we have 6.02 times 10 to the 23 times 2 times more, right? That's all that is. And so this is a ratio, and we use these are conversion factor ratios that we can use to calculate to predict and calculate molecular weights and mass formed, and you'll see, it'll all make sense in a minute. This is a simpler reaction for you to once again make the connection with what those coefficients name. It depends on how we look at it, right? So here we have 2 carbon atoms. We can either say it's 2 carbon atoms or 2 moles, or if we want to actually measure it out, we know that 1 mole is 12 grams. Or we can say 2 times what 1 mole is in mass, 12.05 grams, 12.01 grams, right? Because 1 mole equals that when you weigh it out. That's from the periodic table. So it's really not that difficult. And so those ratios they stay together no matter how we scale it up. And then we may want to know, well, what if I have 500 grams of carbon? How many grams of carbon dioxide am I going to produce, right? Or how much oxygen am I going to need? How many grams of oxygen am I going to need? Or what if I have 70 moles of O2? How much carbon can I burn with that? So from this you get conversion factors, and so you can make the connections between moles of oxygen and grams of carbon dioxide, or moles of O2 and moles of carbon. That comes from the coefficients and the molecular weights and the concept of the mole. So this right here gives you all the conversion factors that can be derived from this balanced equation. First, we know from the periodic table the conversion of moles of a substance or an atom to grams of a substance of an atom. So that's what these are here. We have carbon, oxygen, and carbon dioxide. So we can have moles of carbon monoxide converted to moles to moles, so grams to moles. And so that's from the periodic table here. 12, 32, 2 times O, 2 times 16, and then 1 carbon and 1 oxygen is 28 grams. So those are the conversion factors, and you've done this already. So now you can say if you have 0.04 moles of CO2, then you know that you use this conversion factor to go to grams of CO2, and you set it up in a fashion where you would multiply by 28 grams of CO, and I like to put CO2 here, don't I? Yeah, it's just CO, carbon monoxide, divided by 1 mole of carbon monoxide. The mole and the grams, the moles cancels and the CO cancels, and my answer is going to be in grams of CO. Those are the mole to gram and gram to mole conversion factor, but we also have mole to mole conversion factor because we have carbon and oxygen in a 2-to-1 ratio, right? 2-to-1 ratio carbon oxygen, 2-to-2 or 1-to-1 ratio of carbon to carbon monoxide, and a 1-to-2 ratio of mole of oxygen to carbon dioxide. So if I wanted to know, if I have 0.04 moles of carbon monoxide, how many moles of carbon I need, I can then take simply that mole to mole conversion factor. What did I say? Carbon to carbon monoxide? Yes, that's in a 1-to-1 ratio. So if I have 7 moles of carbon, I'm going to produce 7 moles of O2. But if I have 7 moles of O2, I'm actually going to produce 14 moles of CO, right? So that comes from the coefficients of the balanced equation. Let's mess around with that a little bit, okay? So here we have that same reaction. And I'm asking how many moles of carbon monoxide would produce 10.5 moles of oxygen. So this is a mole to mole conversion, right? So you're given moles of A here. In this case, you have 10.5 moles of oxygen. That's A is O2 in this case here, right? And so I need a conversion factor that relates the moles of A to moles of B. My moles of B here is carbon monoxide. My moles of A, of course, is oxygen. So my conversion factor comes from the balanced equation. There's 1 mole of O2 equal to 2 moles of CO. All right, and so I take this and I put it in here, dividing by the moles of O2, which there's a 1 in front, and multiplying by the moles, 2 moles of CO, which produces, of course, double that 10.5, so it's going to be 21.0 moles of O. Pretty simple, right? This is just a little nicer and neater, all solved for you here. Let's do one more based on the same equation with a different question. 2.75 moles of oxygen would produce how many moles of carbon? So the conversion factor is going to be oxygen and carbon, right? So carbon is 2, oxygen is 1. 1 mole of O2 equals 2 moles of C. If I have 2.75 moles of O2 and I use the conversion factor, I divide by 1 mole of O2 and multiply by 2 moles of C, and I get double that, which is 5.50 moles of C. Okay, here it is neatly worked out. You have that in your slides. And just another one and another one and another one. Okay, so here we have how many moles of oxygen would produce 0.567 moles of CO2. So we have 0.567 moles of CO. Probably I said CO2 again, didn't I? Need to divide by moles of CO. I'm looking for oxygen and multiply by moles of oxygen. Here's a 1 and there's a 2, and so this is half of that, which is 0.2 something, 4 something. Okay, 0.284 moles of O2, and I'm a little sloppy here. This is supposed to be A2. Here it is again worked out. Different reaction. Let's take a look at it, but nothing really changes here, right? So now we have different reactants and different products, and we have different coefficients, right? But it doesn't change the concept. So how many moles of hydrochloric acid would be produced, okay, I gotta fix that, from 2.85 moles of silicon tetrachloride. So 2.85 moles of SiCl4, and so I have 4 moles, I have 1 mole of SiCl4 is equal to 4 moles of HCl. That's the conversion factor. Moles of SiCl4 to moles of HCl. And so I just plug that in here. 4 moles of HCl divided by 1 mole of SiCl4 equals 11.4 moles of HCl. Alright, it's just going to boil down to practicing that a little bit. This is just cleaner here than what I just did on the board or here on the slide. Let's do one more just because these are super fun. How many moles of water would react with 0.783 moles of silicon tetrachloride? Okay, so we have water, silicon tetrachloride. And another thing that's important, all we've done so far is mole to mole, so I don't have to, but you need to figure out what I'm asking for. I might sometimes ask for grams, right? Then that changes things. I don't have a single step conversion factor of grams to moles, at least not from one substance to another. I do have them. I can do grams to moles of water, but I cannot do grams of water to moles of silicon tetrachloride in one step. That would be more steps. So always look at the unit here. Okay, so moles to moles, easy. We're just looking at 1 mole of SiCl4 equals 2 moles of H2O. That's the conversion factor we obtained from the balanced reaction. And now I have 0.0738 moles of SiCl4. I multiply by 2 moles of water, and I divide by 1 mole of SiCl4. And I think it's important that you write that out so I can give you partial credit. And so this gives me 0.148 moles of water, right? We cancel the moles, we cancel the silicon, and we have 3 significant figures, and so this is the right answer. This is just a little neater, again, the solution. And now, as I hinted, if I change the unit, now I don't have moles to moles, I have how many grams of HCl would produce from 2.85 moles of silicon tetrachloride. So now that changes the game a little bit. Now if we remember, we did that reaction, we did that conversion earlier from if I have grams, I have to go from grams of HCl to moles of HCl, and once I'm at mole of HCl, I can do the mole to mole conversion, right? So I know the conversion factor. We have HCl, so 4 moles of HCl equals, looking for silicon tetrachloride, 1 mole of silicon tetrachloride. That's one conversion factor, but I'm also going to have to go from grams to HCl. So we have 1 mole of HCl equals 36.46 grams of HCl. Now I can do this one step at a time. I'm given 2.85 moles of SiCl4 times, now I'll go from moles, now use this conversion factor here, times 4 moles of HCl divided by 1 mole of SiCl4. This gives me moles of HCl. Now I can do this. I can multiply by 36.46 grams of HCl and divide it by 1 mole of HCl. Silicon tetrachloride cancels, the moles of HCl cancels, and my unit's going to be grams of HCl. I multiply that out, I get 416 grams of HCl. Alright, so here's the answer for that. We are going to step things up a little bit now, make it more complicated, so I'm going to take a break. When you come back, we're going to do gram-to-gram conversions, limiting reagents, and theoretical yield.